This is B. Naresh, working as assistant professor in AEC department. Today's topic is self-bias. So before going to this biasing concept, and this biasing methods is approached for transistor to act as a amplifier. And we know that so when the transistor is configured in the active region, it acts as a amplifier. And in that amplifier configuration, we need to maintain a stable operating point in an active region. But depends upon the temperature parameter, the current gain of the transistor, and the reverse saturation current of the transistor, and the VB parameter when we consider the common emitter configuration. So these three parameters are affected with respect to your temperature. So when the temperature is a changes, these three parameters are changes the collector current. If the collector current is a changes, then the Q point or operating point is also triggers towards saturation region or a cutoff region. And whenever the Q point is nearer to the saturation or a cutoff, it loses some amount of the portion of given input signal. So that is the reason we are going to provide a stable operating point irrespective of these three variations like reverse saturation, reverse saturation current of the transistor, and the current gain of the transistor, as well as VB parameter of the transistor, means the potential difference between base and emitter. So for this case, we discussed that three different biasing methods like fixed bias, collector to base bias, and collector to base with emitter resistance. If we consider that collector to base with emitter resistance, if the collector current is changes, the emitter current is also changes. If the emitter current is changes, the voltage drop across the emitter resistance also changes. The change in this voltage drop is becomes means it changes the emitter base junction to be reverse bias. So when this voltage drop across the emitter is the changes, if the emitter base junction becomes your reverse bias. If the emitter base junction becomes the reverse bias, means the transistor does not act in an amplifier. To compensate this change in voltage drop across the emitter resistance, so here we are going to provide a simple biasing method. That method is called as a self-biasing method. So this biasing method itself, it compensates the change in collector current. So that can be absorbed through this voltage drop across the emitter. Means whenever the voltage drop across the emitter is the changes, simultaneously that should be compensated through this potential divider network. Hence, so in this session we are going to discuss. So we are going to discuss the simple biasing concept to overcome the mentioned drawbacks in collector to base bias and a fixed bias, as well as collector to base with emitter resistance. And by using this self bias, we are going to compensate the change in collector current, and we are also going to stabilize the operating point that should be in an active region. And this self bias here, it is also called as a potential divider circuit. And irrespective of your temperature parameters, always we need to satisfy that emitter base junction should be forward bias and collector base junction should be reverse bias to operate the transistor as amplifier. To again, for this case, we need to provide a stabilized operating point or a constant Q point in an active region. For this case, let us consider the self-bias circuit. And here we are going to use a common emitter configuration. And I used NPN transistor. and this is N type of material, P type of material, this is N type material. And this terminal is represented as collector, this terminal is a base, and this terminal is represented as emitter. So so whenever the collector current is the changes, and proportionally the emitter current is also changes. Why? Because of that, based on the construction of the transistor, we know that the IC is approximately equal to emitter current, means the collector current is approximately equal to emitter current. And due to the temperature variations, either any one of the parameter is affected, like either a current gain or a VBE parameter or a reverse saturation current. It affects the change in collector current. If the collector current is a changes, the emitter current is also changes. If the emitter current is a changes, the voltage drop across this emitter resistance is also changes. If you observe this VBE parameter, means from this representation we can write, so it is represented as the potential difference between base and emitter, means we can write like this: VB minus V. VBE means the potential difference between base and emitter. It is represented as VB minus V. In a previous circuits like fixed bias or a collector to base or collector to emitter feedback resistance bias, and in that collector to base with emitter resistance, if the voltage drop across the emitter is the changes, or in the self bias also, if IC is the changes, IE is the changes, means the voltage drop across the emitter is also changes. If VE is increases, the junction becomes, means we consider as your VB is a constant. While the VB is a constant, if the emitter means voltage drop across the emitter is increases, it becomes this particular junction, means emitter base junction becomes reverse biased. If the emitter base junction becomes a reverse bias, the transistor does not act as an amplifier. Why? Because of that, we need to show that the transistor is always operates in a active region to satisfy the amplifier principle. To compensate this or to make always this emitter base junction is a forward bias, that can be done through a potential divider network voltage. This VT drop always to make this emitter base junction should be forward bias, even though the voltage drop across the emitter is changes. So how much voltage drop is increases, that should be compensated through this potential divider network voltage to stabilize a constant collector current across the output of this transistor. If we maintain a constant collector current, means the operating point is also becomes stable. That is the reason that can be done through a biasing method. That biasing method here it is called as the self bias. The circuit itself it compensates the change in collector current in terms of this potential divider network voltage, and due to this potential divider network voltage, always it makes the emitter base junction is forward bias, and already the collector base junction is reverse bias. Hence, the transistor is always act in a active region. So, if the transistor is an active region, we can say that it acts as a amplifier principally. And to satisfy this voltage divider network, and here we use that a potential divider network that is made with two resistances here, R1 and R2. This R1 and R2 is a biased with VCC, and this is a positive polarity. Then it becomes, and this node makes that your emitter base junction is forward bias. Similarly, output side means the collector base junction, we need to maintain reverse bias here. For this NPN transistor, the collector is made with N-type material. Hence, this N-type material is biasing through a biasing resistance, that is collector resistance, and it is biased from the positive pole of the battery. When this N-type material is biased with a positive terminal of the battery, we can say that this particular junction is acts as a reverse bias T. So with respect to this biasing and the voltage divided network, we made that your input junction means emitter base junction is forward bias and collector base junction is reverse bias. Now we need to analyze how it maintains a stable operating point or how it maintains a constant collector current by using this self-bias mechanism for a transistor. And before going to this, first we need to convert the equivalent voltage, how much voltage drop is produces with respect to this potential divider network along with the biasing source, that is VCC. For this case, we need to apply a Thevenin's theorem. So by using a Thevenin's theorem, we need to find out the voltage drop across the base with respect to this biasing components, that is R1 and R2 through with a biasing source is VCC. And similarly, and how much equivalent resistance is generates through this biasing component for the base side. For this case, we need to apply a Thevenin's equivalent principle, equivalent theorem principle. By applying this Thevenin's theorem, we need to find out the voltage drop across this node, that is represented as Vt, and equivalent resistance across the base side in terms of these two biasing resistances, that is R1 and R2. Apart from that, so depends upon this biasing principle, it generates a potential difference between base and emitter, that is represented as VBE parameter. Similarly, at the output side, the potential difference between collector and emitter is represented as VCE. So means that this is potential difference between collector terminal and emitter terminal. Across this biasing resistance, it allows the current. That current is represented as collector current, that is IC. And similarly, across this RE, it allows the current. That current is represented as emitter current. For this base side, it allows the base current, hence it is represented as IP. So now by using the self bias, now we are going to find out the equivalent circuit, Thevenin's equivalent circuit, how much voltage drop and how much base resistance is generates with respect to this potential divider network along with the biasing source is VCC. So first, I am going to find out how much node voltage is generated. Means for this case, I consider this input loop. So from this representation, I consider this part. And in this side, I am going to find out how much voltage drop it generates. Then I can apply the KVL principle to determine the node voltage across the base side. So means, so we need to find out from this node voltage to VCC node. Similarly, from VT node to ground potential along with the biasing component is R2. For this case, VT to VC node through the biasing resistance is R1. Hence, here I am applying the KVL principle. So means we need to write the potential difference between from this node to this node, that is represented as, this node is represented as a VT, and this node is represented as VCC. The potential difference from this node to this node is represented as VT minus VCC through this biasing resistance, that is R1. Hence, I represented as VT minus VCC by R1 along with another node. From this VT node to another potential is a ground potential. Now we need to find out how much voltage, means how much voltage drop it generates here. Hence, this node is represented as the VT, and we know that the lower potential node is represented as 0. Hence, the potential difference between from this node to this node is represented as Vt minus 0 along with the biasing resistance is R2. Hence, Vt minus 0 by R2, that is equal to 0. From this expression, we need to find out how much Thevenin's voltage, how much equivalent voltage is generates across this node. So just you can expand these terms. How to write this term? So means this is Vt by R1 plus Vt by, sorry, this is Vt by R1 minus VCC by R1 plus Vt by R2, that is minus 0 by R2 means something, 0 by something is 0, that is equal to 0. In this case, then we take the common terms. Vt is a common term, means if the Vt is a common term, we can represent like this: 1 by R1 plus 1 by R2, that is equal to, I taken this is outside, so means that is VCC by R1. Now I can take the LCM. So this is Vt, so means this is R1 plus R2 by R1 R2, that is equal to VCC by R1. From this, if you want to calculate this Vt voltage, this is VCC by R1 into R1 R2 by R1 plus R2. This R1 R1 is a get cancel. So from this, the equivalent node voltage along with this potential divider network and the biasing source, that is represented as VCC times the R2 divided by R1 plus R2. And this is potential divider network R2 by R1 plus R2. So hence, here I represented as the same parameters. So from this, I calculated the Vt is equal to VCC times the R2 by R1 plus R2. So means that at this point, it generates some amount of the voltage with respect to your biasing source, that is VCC, along with this potential divider network R1 and your R2. Due to this combination, the node voltage across the base is represented as VCC times the R2 by R1 plus R. So whenever the collector current is changes, then simultaneously the emitter current is also changes. If the emitter current is changes, the voltage drop across this emitter resistance is also changes. This change in voltage drop across the emitter resistance to make this emitter base junction is reverse biased here. To compensate this one, irrespective of this change in the voltage drop across emitter resistance, we need to make the emitter base junction is always forward bias. And that should be done through this threshold voltage or a Vt voltage, a Thevenin equivalent voltage. So with respect to this parameter, irrespective of this the change in voltage drop and itself This makes your emitter base junction is always forward biasing. Then, apart from that, now we need to calculate how much equivalent resistance is flow or biased with the base terminal. To identify this equivalent resistance at the input side, this R1 is removed from the VCC and it should be connected to ground node. So if R1 is removed from the voltage source and it is connected to ground node, from this node we can say that this R1 and R2 is becomes the parallel combination here. So from that circuit, to determine the equivalent resistance, and that is also represented as the base resistance, whenever this R1 is removed from the VCC source, from this node we can observe that this R1 resistance and R2 resistances are parallel. From this representation, this RB is represented as R1 R2 by R1 plus R2. That is nothing but the parallel combination of R1 and R2 resistance. Now, by using this, the Thevenin's equivalent voltage and Thevenin's equivalent resistance, we need to redraw the Thevenin's equivalent circuit with respect to this Thevenin's voltage and Thevenin's resistance. So hence, by using these two parameters, I am going to redraw this self bias in terms of a Thevenin's equivalent circuit. For this case, let us consider this is about a self bias circuit. Now we are going to redraw in terms of a Thevenin's equivalent circuit. So for this case, and we observe that one with respect to from input side from this VCC node to R1 towards VT node and R2 node toward this ground potential is converted in terms of Thevenin's equivalent voltage and Thevenin's equivalent resistance. Hence, the source is represented as the voltage source here, the input side. The voltage source is represented as VT, but we know that where the VT is represented as VCC times the R2 by R1 plus R. But you should remember this in a self bias, the Thevenin's equivalent voltage in terms of this biasing components and the sources, it is represented as VCC times the R2 by R1 plus R. And this R1 and R2 is replaced with the equivalent base resistance or the Thevenin's equivalent resistance that is represented as RB. Again, from this, we know this the RB is the parallel combination of R1 and R2. So hence, so this node contains the Thevenin's equivalent voltage and then starts from the base resistance that is RB and the resistance directly connected to base of NPN transistor. Now coming to this collector side, if you observe this side, the collector is biased with a collector resistance and it is biased with a VCC source. Hence, here also the collector is biased with the VCC through a biasing resistance that is RC. Similarly, at the emitter side, emitter is biased with a lower potential, means it is grounded, with the biasing resistance is RE. So here also emitter is biased with a lower potential with the biasing component that is R. And this is the input side, that is a Thevenin's equivalent voltage, that is in terms of your biasing sources along with a potential divider network, that is R2 and R1 resistances here. Now by using this Thevenin equivalent circuit, now we need to identify the Q point or a operating point. So we know that the operating point is a functioning with respect to a output current and output voltage. And for this configuration, the output current is represented as collected current and output voltage is represented as VC. Means the potential difference between collector and emitter. And in between, for the, across the emitter base junction, the potential difference between base terminal, this is the base terminal, and this is the emitter terminal. In between this, the voltage drop is represented as VBE, that is also called as the potential difference between base and emitter. Now we are going to analyze the circuit operation to determine the operating point in terms of collector current and output voltage, that is VCE. So for this case, first to determine, we know that IC is represented as beta times of IB plus 1 plus beta times of ICBO. And from this common emitter configuration, we know that the collector current is represented as beta times of IB plus 1 plus beta times of ICBO, where this ICBO is represented as a reverse saturation current when the collector base junction is open circuited. And we know that the reverse saturation current is always much less than of 1. Hence, IC is approximately equal to beta times of IB. And from this relation, we need to find out if you want to determine this collector current in terms of the base current. Now we need to identify that how much base current is the flows with respect to biasing components and sources. That is the reason. First, I'm going to observe how much base current is the flows with respect to biasing components, biasing resistances, and biasing sources. To determine this base current, here I'm going to apply the loop at the input side, or I'm going to apply the KVL principle at input loop. So if you consider the input loop, and this is the input loop, starts from the VT towards base, biased with the base resistance, and towards emitter, emitter to emitter resistance, and towards ground potential. If you want to write the KVL principle here, and we need to start from the source is VT, hence VT is equal to the voltage drop across this base resistance is represented as IB times the RB, along with the potential difference between base and emitter is VBE, and along with the voltage drop across the emitter resistance is IE times the R. Hence, the VT equal to IB times RB. So means this is voltage drop across the base resistance, and the potential difference between base and emitter is VBE, and the voltage drop across the emitter resistance is IE times the R. From this, we need to identify how much base current is flows. To observe this base current, we need to convert first the unknown parameters in terms of the required parameters. So here we are going to observe the base current, and here I'm going to convert the emitter current in terms of base and the collector. From the transistor construction, we know that IE is equal to the summation of base current and collector current. Hence, I'm going to substitute here this IE is equal to the summation of base current and collector current. Hence, VT is equal to, this is IB and RB plus VB is a VBE. Just IE is replaced with IB plus IC times RE. Again, here IC is unknown. I'm going to convert again in terms of IB. So for this case, first I expand these terms, IB times of RB plus VB is a VBE. This is IB times of RE plus IC times of RE. And by using this one, so we know that IC is equal to beta times of I. That is the reason IC is replaced with beta times of IB. So if you observe this mathematical relation, all the terms are only the known parameters, and only the one unknown parameter is IB. Now we need to determine how much base current is the flows with respect to this biasing source and the biasing components. And from this relation, we need to identify the base current. So for this, Vt is equal to, if Ib is a common, from this Rb, and from this the Re resistance, and from this term beta times of Re plus Vbe. So now we can solve this one, that is Vt minus Vbe by Rb plus Re plus beta times of Re, that is equal to your Ib. Hence, so we observe the base current is represented as, it is a ratio of the potential difference between Thevenin's voltage and VBE to the RB plus RE plus beta times of RE. So we observe how much base current is flows with respect to this biasing method here. Now we need to determine the how much collector current is generates with respect to this self-biasing method. Hence, we need to use, we know that the collector current from the common emitter configuration, the collector current IC is represented as beta times of IB. So, just we need to substitute the IB value here to determine the collector current across this self-biasing method. Now, again, if you want to define a operating point, the Q is the functioning with respect to output voltage, that is VCE, and output current, that is IC. So just now we got this collector current. Now we are going to calculate the VCE parameter at the output side. Hence, I'm going to apply the KVL principle at the output side. So let us consider the same Thevenin's equivalent circuit. Now we are going to apply the loop at the output side, means we need to start from VCC to collector through the biasing resistance, that is RC, and again collector to emitter, emitter to this emitter resistance, and towards lower potential. So hence I consider this loop from VCC to ground potential, lower potential. If you consider this output loop, then we need to write the KVL loop, means the starting source, means entering source is VCC, that is VCC equal to the voltage drop across this collector resistance is represented as IC times of RC plus the potential difference between collector and emitter is represented as VCE, along with the voltage drop across the emitter resistance is represented as IE times R. That is the reason. If you observe the KVL loop equation, VCC equal to, this is voltage drop across this RC along with VCE along with the voltage drop across RE, that is IE times of R. So from this relation, we need to determine how much output voltage is generated, VCE parameter, that is between collector and emitter. So before going to this, and we know that, and based on the transistor construction, IE is represented as the summation of base current and collector current. And based on the transistor construction, we know that very small current flows across the base terminal compared with the collector terminal. Hence, so why? Because of the doping levels of the base is very lightly doped, and the region of the base is also very thick. Due to these doping levels, the base terminal allows very small amount of current. That is the reason IE is approximately equal to IC. Hence, I replaced this IE with IC term. Now from this, we need to calculate the VCE parameter. So if you want to observe the VCE parameter, so from this relation, the VCE equal to VCC minus. So in this case, if IC is a common, that is RC plus RE, then that is VCE, that is equal to VCC. So from this, I'm going to calculate this VCE. Hence, VCE equal to VCC minus this term is outside IC times RC plus RE. So this is the output voltage between collector and emitter in terms of your biasing components and the biasing sources. So up to this point, we observed the Q point parameters, the collector current and the output voltage between collector and emitter. Now we need to identify that is it it maintains a stable Q point or not. For this case, we are going to calculate the stability factor S. So from this biasing concept and depends upon the temperature parameter, and we know that if temperature is a changes, the reverse saturation current of transistor and the current gain of the transistor, if I consider the common emitter, the current gain is represented as the beta. And again, if it is the common emitter, the another voltage is at the input side, that is V. These three parameters are affected with respect to your temperature. Hence, these three parameters also affect the change in collector current. So means we need to stabilize or we need to maintain a constant current, collector current, irrespective of these three parameters or irrespective of your temperature. We need to identify the three stability factors. Means we know that S, S dash, and S double dash. The S means we defined as the S is defined as the rate of change of collector current is changes with respect to the rate of change of reverse saturation current while making the another two parameters beta and VB is considered as constant. So this is the factor, means how much collector current is the changes with respect to the change in reverse saturation current by making this beta and VB is constant. And again, we know that if stability factor is equal to unity factor, we can say that that particular biasing is more suitable to design the transistor is acts as a amplifier or a perfect amplifier. Now we are going to observe this self bias is makes a good stability factor or not. For this case, here I am going to consider the self bias, again the Thevenin's equivalent circuit, to identify, and from this representation, and this is the definition for stability factor, and from this common emitter configuration we can also identify the stability factor is represented as 1 plus beta by 1 minus beta times of dou IB by dou IC. If you observe this mathematical relation of stability factor, we need to identify the base current and how this base current is changes with respect to the change in collector current. So that is the reason. First, we are going to observe how much base current is generates with respect to this biasing method. That is the reason. Again, I am going to apply the KVL principle at the input loop. And from this input loop, we need to write the KVL loop equation. Means we need to start from the VT. So VT equal to voltage drop across the RB is represented as IB times the RB, and the potential difference between base and emitter is represented as VBE, and the voltage drop across the emitter resistance is represented as IE times the RE. Hence, I considered the same equation. So VT equal to, this is voltage drop across the base resistance IB times of RB. Along with this, the potential difference between base and emitter is VBE, and the voltage drop across the emitter resistance is IE times the RE. Now again we know that IE is represented as the summation of base current and collector current. Hence, I'm going to replace this IE with IB plus IC. So IB times of RB is the same, VB is the VBE, and this IE is replaced with the summation of base current and collector current. Now I can expand the terms here. So VT is equal to IB times of RB plus VBE plus IB times of RE plus IC times of RE. So from this, we can write this IB VT is equal to, if IB is a common, this is RB plus RE plus IC times of RE plus VB. So from this, we need to calculate IB value. So means IB is equal to VT minus VBE by RB plus RE and minus IC times of RE by RB plus RE. So hence, I represented the same parameter here. So from this, we determine like this. IB is equal to the potential difference between VT and VB to the RB plus RE minus IC times of RE by RB plus RE. Now by using this base current and to identify the stability factor, we know that the stability factor is S is equal to dou IC by dou IC na, that is equal to 1 plus beta by 1 minus beta times of dou IB by dou IC. Hence, to observe the stability factor, we need to observe how much base current is affected with respect to the change in collected current. Hence, we need to apply the differentiation for this base current with respect to the collected current. Hence, dou IB by dou IC becomes, and by making, while observing the stability factor, we know that the another two parameters, the temperature dependence parameter, that is beta and VBE is constant. Hence, here this VT, if you observe the VT expression, we know that VT is equal to VCC times the R2 by R1 plus R2. In this, where VCC is a constant and R1, R2 is also, we made the fixed resistances. Hence, VT is also becomes constant. And the constant differentiation is 0. And VB is also constant, hence the differentiation of the constant is 0. Now, we are going to differentiate with respect to IC, hence the dou IB by dou IC becomes minus RE by RB plus RE. This is the rate of change of base current with respect to the rate of change of collector current. That is dou IB by dou IC equal to minus RE by RB plus RE. Now we need to substitute this dou IB by dou IC value in a stability factor, and this is the stability factor. S is represented as 1 plus beta by 1 minus beta times of dou IB by dou IC. Now I can substitute this dou IB by dou IC value here. Hence, it becomes S is equal to 1 plus beta by this 1 minus, and this is minus. Minus of minus, it becomes plus beta times of RE by RB plus R. Now we need to show that how we can show that a good stability factor by using the self bias. For this case, I'm going to simplify this equation, and in this case, just take this LCM here. So now what happens, LCM means S is equal to 1 plus beta by. So if you take the LCM, it becomes RB plus RE plus beta times of RE by RB plus RE. And this relation I written here. So again I take this is outside, top side. So hence 1 plus beta times of RB plus RE by RB plus RE plus beta times of RE. And in this again, here from these two expression, RE is a constant, hence I taken the RE is a common. So this is 1 plus beta times of RB plus RE by this is RB is RB plus from these two relations I made RE is a common term, hence I made RE is a common term, that is 1 plus beta times of RE. So from this expression, if if you observe this one, in this, if the denominator and the numerator is divided with a RE term, means I'm going to approach the stability factor is equal to unity factor. To approach this stability factor is a good stable factor, here I'm going to divide the denominator and numerator with a RE term, hence the equation, that above equation becomes 1 plus beta, that RB, so that is S is equal to 1 plus beta times of RB plus RE by RB plus 1 plus beta times of RE. And for this expression, I'm going to divide RE term in a denominator and the numerator. Hence, 1 plus beta by this RB by RE, and RE by RE becomes 1. Again, this RB by RE plus 1 plus beta times of RE by RE means it becomes 1. And in this relation, if we maintain the ratio, means what is the ratio? RB to the RE ratio is much less than 1. If we maintain the ratio of RB and RE is much less than 1. So if we assume like this, if RB by RE is much less than 1, what happens here? So we neglected this term, means this is 1 plus beta times of 1 means it becomes 1 plus beta by. If RB by RE is much less than 1 means this is 1 plus beta, it is always greater than 1. Hence, it is also very small compared with this 1 plus beta. Hence, again, this is also becomes 1 plus beta. Means, so under this condition, your stability factor is approximately equal to unity value. Hence, so that is the reason. If RB by RE ratio is much less than 1, the stability factor shows that unity factor. So we know that when the stability factor is very small, means value small factor that is equal to unity factor, we can say that that particular biasing method is a good biasing method to design a amplifier by using the bipolar junction transistor. So from this observation, we identified that based on the different biasing methods. So what we discussed in the biasing methods like the fixed bias or collector to base bias or collector to base bias with a emitter resistance and this self bias. Out of all these biasing methods, the self bias is a more suitable bias method to design a amplifier by using the bipolar junction transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.